Welcome to our Bioprocess Engineering online tutorial on the microbial cell's kinetics. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. In this tutorial, you will explore the kinetics of microbial cells and fermenters, gaining insights into their growth, substrate consumption, and metabolite production. We will address the following questions. Why is microbial kinetics important for bioprocess engineers? What are the different microbial rates? What are the most common kinetic laws for cell growth, metabolite production, and substrate consumption? Microbial cell kinetics refers to the study of how microorganisms, such as bacteria, yeast, and fungi, grow, consume nutrients, and produce metabolites over time. For bioprocess engineers, understanding microbial kinetics is essential for analyzing microbial transformations in fermenters, including the rates of nutrients consumption by microbial cells, the cellular growth rate, the production rates of metabolites and recombinant proteins. Microbial kinetics plays a fundamental role in fermenter performance, influencing productivity and conversion yield. Identifying microbial kinetic laws is essential for the scale-up and optimization of fermentation processes. Microbial kinetics governs how concentration time variations in cell growth, substrate consumption, and product formation evolve across different fermentation modes, including batch, continuous, and fed batch systems. Understanding these dynamics is key to improving process efficiency, maximizing yield, and ensuring consistent production at an industrial scale. Microbial kinetics plays a pivotal role in the development of knowledge-based simulation models for fermentation processes. Derived from experimental data collected at the laboratory scale, these simulation models are designed to predict dynamic changes in nutrients, cells, and metabolites concentrations within industrial fermenters. This enables the optimization of key operational parameters, which are essential for the efficient scale-up of bioreactors. Microbial cells' kinetics are generally described by specific rates expressed per unit amount of dry cell mass. For a microbial reaction consisting in the transformation of a substrate S into cellular biomass X and a metabolite M, the three following rates are introduced. The specific rate of substrate consumption, QS, in gram substrate consumed per gram cell an hour. The specific rate of cells growth, mu, in gram cells produced per gram cell an hour, and the specific rate of metabolite production, QM, in gram metabolite produced per gram cell an hour. Microbial specific rates vary throughout the fermentation process, influenced by the cell's environment. These cellular rates are primarily dependent on the concentrations of nutrients and metabolites, as well as the temperature and pH of the medium. Additional factors such as osmotic pressure, ionic strength, and shear stresses can also impact microbial kinetics. The dependence of microbial specific rates on their environment is governed by kinetic laws. These laws are mathematical relationships that predict specific rates based on the composition of the surrounding medium. The most commonly used kinetic laws describe cell growth, sugar and oxygen consumption, as well as metabolites and proteins production. These laws express specific rates as functions of nutrients and metabolites concentrations, or they establish relationships between the rates. Industrially used microorganisms include bacteria, yeast, and fungi, each with unique growth characteristics dependent on the composition of the fermentation medium. When cultivated in fermenters, several distinct growth phases can be observed. A very slow initial lag phase, a rapid exponential type growth phase, a slower, reduced growth phase, and potentially a final stationary or growth-arrested fermentation phase. The initial slow lag phase corresponds to the adaptation of the inoculated microbial cells to their new medium environment. This latency phase is conceptualized as follows. Initially, the inoculated cells are in a dormant state, with minimal metabolic and growth activity. These latent cells XLAT gradually transition into actively growing cells XG. The rate of this transition, denoted as RLAT, is measured in grams of cells per liter per hour and is assumed to be proportional to the concentration of latent cells XLAT, with KLAT representing the first-order transition rate constant. The value of KLAT determines the duration of the latency phase. A higher KLAT results in a shorter latency phase. Once microbial cells have adapted to the fermentation medium, the cell concentration typically follows an exponential growth pattern. During this phase, cells grow at their maximal specific growth rate, mu max, measured in grams of cells produced per gram of existing cells per hour. In a batch fermentation, the instantaneous biomass balance leads to a differential equation that expresses the time derivative of the biomass concentration, dx over dt, as equal to mu max, x. Integrating this equation results in an exponential increase in biomass concentration, x equals x0 exponential, mu max t, where x0 is the biomass concentration, at the start of the exponential growth phase. The subsequent growth decelerating phase is typically driven by limitations in the concentration of consumed nutrients, particularly the sugar substrate. The classical law that describes the relationship between substrate concentration and specific growth rate is the Monod equation. It is expressed as the product of the maximum growth rate mu max and a substrate limiting term, mu equals mu max, times S over Ks plus S, where S is the substrate concentration and Ks is the half saturation constant for the substrate. As a first approximation, the substrate concentration is considered limiting when it falls below 10 times the value of Ks. The growth decelerating phase can also result from the inhibitory effects of excreted metabolites. The simplest form of metabolite inhibition follows a linear type described by the inhibition term 1 minus m over m max, where m is the metabolite concentration and m max is the maximal concentration of excreted metabolite at which growth is arrested. More complex, nonlinear metabolite inhibition patterns can also occur. For example, the rate-limiting term may take the form 1 minus m over m max to the power alpha, where alpha determines the shape of the inhibition curve. Depending on the value of alpha, the mu versus m curve can exhibit either upward or downward concavity. The final growth-arrested phase can occur when an essential nutrient is depleted in the medium or when a metabolite reaches its limiting inhibitory concentration. Alternatively, in fermentations that produce non-growth-associated metabolites or proteins, the growth-arrested phase arises from the transition of cells from a growth state Xg to a production state Xp. This physiological shift is typically triggered by the addition of an inducer, a temperature change, or nutrient limitations. The rate of this transition, denoted as Rgp third, is measured in grams of cells per liter per hour. It is assumed to be proportional to the concentration Xg of growing cells. The constant Kgp represents the first-order transition rate constant. The value of Kgp determines the duration of the transition to the growth-arrested state. A wide range of products are industrially produced through microbial fermentation, all derived from the complex metabolic pathways of the microbial cells used. Fermentation products can be classified into four main categories. Small metabolites, such as organic acids, amino acids, nucleotides, alcohols, esters, antibiotics, vitamins. Macromolecules, mainly polysaccharides, peptides, proteins, DNA. Cells, for instance, baker's yeast, starters. Fermented foods such as yogurt, beer. Each of these products follows distinct production kinetics throughout the fermentation process. The production of metabolites or recombinant proteins can occur during different growth states of microbial cells. Growth-associated production is the simplest, though less common, scenario for metabolite production. For example, metabolites like ethanol or lactate are byproducts of cellular growth metabolism. In this case, metabolite production takes place during the growth phase and ceases once growth ends. The rate law for growth-associated metabolite production states that the specific production rate of the metabolite Qm, measured in grams of metabolite, per gram of cells per hour, is proportional to the specific cell growth rate mu. The stoichiometric coefficient, Ym over x, represents the grams of metabolite produced per gram of cell biomass. For growth-associated metabolites, an alternative scenario involves a reduction in metabolite excretion at low growth rates. This occurs, for example, with the excretion of ethanol, acetate, or lactate by aerobically grown bacteria or yeasts. Under high sugar concentrations, metabolites are excreted due to an overflow of sugar in the glycolytic pathway, a phenomenon often referred to as the Crabtree effect. The reduction in metabolite excretion at low sugar concentrations is modeled by introducing a sugar concentration-dependent stoichiometric coefficient, Ym over x, expressed as a sigmoid function of sugar concentration S, Ym over x equals Ym over x max, S power n, divided by Km plus S power n, where Ym over x max represents the maximal value observed at high sugar concentrations, and Km is a constant. This sigmoidal relationship is characterized by a threshold sugar concentration, below which metabolite excretion becomes negligible. The constant Km can be adjusted to simulate the threshold sugar concentration of the microbial cells. More commonly, the production of metabolites or recombinant proteins begins during the growth phase, but continues into the growth-arrested phase. Non-growth associated products are typically not produced during the initial fast cell growth phase. Instead, production occurs at a reduced growth rate, or after cell growth has arrested. The simplest proposed kinetic law for non-growth associated products includes two terms: a growth-associated term, proportional to the growth rate, a constant production rate term during the growth-arrested phase. However, this two-term rate equation has limited applicability. It does not account for the reduced production rate at high growth rates, nor does it consider that the production rate after growth arrest can vary significantly with changes in medium composition. A more efficient kinetic model for microbial production of non-growth associated products is achieved by considering the two physiological state model. This model accounts for the transition of cells from the growth state Xg to the production state Xp. The model includes specific rate laws for cells in the production state. For example, a general kinetic law for the specific metabolite production rate, Qp, is the product of the maximal specific production rate, Qp max, a substrate limiting term at low substrate concentrations, and a metabolite inhibiting term at high metabolite concentrations. Industrial fermentation media provide the essential nutrients required for microbial growth and metabolism. These nutrients include carbon sources, glucose, sucrose, lactose, starch; nitrogen sources, ammonia, ammonium salts, nitrate salts, urea, amino acids, protein hydrolysates; phosphorus sources, phosphates; minerals. In microbial fermentation kinetics, the primary focus is on the consumption rate of the carbon source, typically sugars. For aerobic fermentations, oxygen consumption is also a key parameter to evaluate. For growing cells and fermenters, the commonly used rate law for the specific substrate consumption rate, QS, expressed in grams of substrate per gram of biomass per hour, consists of two terms: the growth-associated consumption rate. This term is proportional to the cell growth rate, mu, with Ys over x representing the stoichiometric coefficient in grams of substrate consumed per gram of biomass produced. The maintenance-associated consumption rate. This term, denoted as MS, represents the substrate consumption required for cellular maintenance and corresponds to the substrate uptake rate at zero growth. At high growth rates, the contribution of the maintenance term is typically much smaller than that of the growth-associated consumption. This rate law applies to all major consumed substrates, particularly sugar and oxygen. For fermentations involving the production of a non-growth-associated metabolite or protein, the specific substrate consumption rate includes an additional term related to product formation. When using a two-state model that distinguishes between growing XG cells and producing XP cells, the overall substrate consumption rate, QS, accounts for both cellular states. QS equals Ys over X, mu, plus MS plus Ys over X, QP. In this model, the substrate consumption rate of growing cells includes both growth-associated and maintenance terms, while the substrate consumption rate of producing cells is proportional to their specific product formation rate, QP, with Ys over P, the stoichiometric coefficient, expressed in gram substrate consumed per gram product. In this tutorial on microbial cell kinetics, you explored the key kinetic laws used by bioprocess engineers to model the time-dependent variations in substrate, biomass, metabolite, and protein concentrations in fermenters. These kinetic laws include specific growth rate laws, incorporating substrate limitation and metabolite inhibition terms, metabolite and protein production rate laws, accounting for both growth-associated and non-growth-associated productions, specific substrate consumption rate laws, considering contributions from growth-associated consumption, maintenance, and product formation. The laws may also include transition rates between the latent, growing, and producing states of cells. These kinetic models provide a fundamental framework for understanding and optimizing microbial fermentation processes. If interested, you can gain a deeper insight in microbial fermentations by enrolling to one of our 2 online courses: Microbial Fermentation Processes, Optimize Fermenters Operations, and Simulation, Scale-Up, and Optimal Operation of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.